Hello everyone, my name is Hossein Matin. I will be presenting um, the stochastic analysis of the optimal velocity dynamical model and its corresponding probability density function. This is a work with Professor Richard Sowers. Let me start with a brief introduction of the dynamical model of interest. We have n vehicles moving in the right direction, and the dynamics of the acceleration or deceleration can be defined based on a function v uh, of the distance between the two vehicles and the current velocity of the nth vehicle. Alpha uh, is a preset constant by the factory, and the performance of the model strongly depends on alpha. So the way that this dynamic works, very briefly, is due to the distance, the acceleration and decelerations are defined based on the distance between the two vehicles and the current velocity. But uh, function v, it's easy to see in the analysis that it should be monotonically increasing and bounded and sufficiently smooth. Due to the properties of this model and the behavior of this model, it is considered as a proper basic model for dynamics of autonomous vehicle, of course, with some modifications. Function v, which we consider in this work, is a hyperbolic tangent function, and as we can see here, it satisfies all of the required properties. We are interested in the stochastic version of this dynamical model by adding some Brownian noise to the velocity. This can be as a result of road, weather, or mechanical failure condition which affect the velocity of the vehicles. We start by study of interaction between the first two vehicles, as this is a key point in understanding how the noise will propagate in the entire platoon. A very important observation here is that the source of the noise in the y coordinate is basically the Brownian noise, while in the x coordinate is a perturbation in y. And this will create some sort of the different speed of propagation of the noise along different coordinates. Let's start with a deterministic system. In fact, let's epsilon to be 0. In this case, we do have the equilibrium solution, which is asymptotically stable. Consider the case in which y is negative, and this means that the second vehicle is moving faster than the first vehicle. So the distance is getting closer. Therefore, the second dynamic is uh, imposing that the derivative of the y should be positive. In other words, y should start increasing, as we can see here. Equivalently, the second vehicle slows down until the point that y becomes 0 and the distance starts increasing until it hits the equilibrium point. Another scenario is when y is positive, but the distance is too large, in this case, it's infinity, and therefore the second dynamic uh, uh, forces that the derivative of y to be negative, or it starts decreasing until it hits 0, then the or distance becomes starts decreasing until it hits the equilibrium point. So to understand the behavior of this dynamic a little bit better, it's interesting to notice that this system is in fact an energy system with some sort of dissipation. Consider the Hamiltonian in a classical way, in which P is defined this way based on a particular definition of a dynamic. It can be shown that P is always positive in this case. It can also be shown that the Hamiltonian is decreasing, as can be seen here. And this means that there is sort of dissipation in the energy of the system, which this sort of dissipation helps to show the boundedness of the solution as well as the stability of the solution. Let's move on to the stochastic version of this dynamical model. We start with some sort of stochastic stability, or more accurately, we can show that uh, the chance that the solution of the perturbed system exit some theta neighborhood of the solution of non-perturbed system is pretty slim, depends on the exponential of minus epsilon squared, given that the initial points are close to each other. So this can also, such results can also be interpreted as a stochastic stability of the solution in some bounded time interval. In fact, we can control the behavior of the solution of the stochastic perturbation based on by controlling the epsilon. If you look at the trajectories of some illustration of these trajectories, we can see that by controlling epsilon, in fact, we can control the neighborhood of this perturbation. In particular, if we start with from the equilibrium point, then the trajectories will remain in a neighborhood of this point for some time. But the question is that how long does it take the process to leave this neighborhood, or how can we characterize this neighborhood? One way to answer this question is through the transition density function. Transition density functions in general explains the behavior of the solution, which in this case is a Markov process. In order to show how we can extract some information, let's start with some simple system in which we replace our nonlinear drift term by a constant drift term b. And it's easy to see that the solution in this case is a Gaussian process with known expectation and covariance. Let's consider a scenario here. Suppose that this system starts from x0, y0, and in a very small time interval, since the covariance is small, we expect that this process cannot go far from the initial point. And calculations, in fact, confirm this guess and shows that starting from z0, after the probability that after a small time, the process is in a pretty tight neighborhood of the initial point is about 80% in this case. And if time is larger, then the covariance is larger, and as we can calculate the probability that the process is in some neighborhood A2 here is pretty slim, and it's only 8%. Now the question is that can we find the transition density function in general case? The answer is yes, and the general idea to construct such transition function is to start from a simple Gaussian kernel and evolve that to construct the transition density function. In our dynamical model, if we drop the nonlinear drift term b here, then the solution would be a Gaussian process with this Gaussian density. Then it turns out that the general density, which is denoted by P here, can be calculated from PG and its convolution in both time and space with some other function phi, where function phi is calculated recursively based on the nonlinear derivative term, which was dropped from PG, and its convolution by the previous iterations. So this is the way that we can construct the in fact, the general transition density function. Uh, the proof of this is pretty complex, and it includes some of the steps as follows. We need to show that this series converges, and uh, we need to also show that the p that has been calculated in this way is in fact a density function. Uh, it means that we have to show that this is 2 times continuously differentiable, and also we have to show that when as time t goes to 0, uh, p behaves in a Dirac form, and also we have to show that mm, mm, we can actually change the order of differentiation and integration in the previous formula. This is a complex proof, and it is included in our paper. Thank you for your attention, and please let me know if you have any questions.